Hello students, welcome to yet another physics session, and this time around we will start on our topic, that is topic number 9 in physics book 4 on photoelectric effect. We are still on the atomic physics and we are still dealing with the electrons. We still have 2 more topics to clear the whole syllabus of physics, and I hope we shall walk this journey step by step together. In photoelectric effect, there are a few objectives we need to achieve by the end of the topic, and one is you should be in a position to explain what is photoelectric effect, and 2, you need to explain how photoelectric effect takes place. 3, you should be in a position to explain the factors that affect photoelectric effect, and finally you should give the uses. I should be able to explain the various ways in which photoelectric effect is put into practice or it's applied in our day-to-day lives. So welcome to this topic. Many times we've seen a situation where you get close to a door and the door opens automatically. We've seen a situation where we have some security lights where when you get close to that security light, it goes on, and if you are if you are beyond a certain radius, then that bulb goes off. By the end of this topic, you should be able to explain what really happens in such a situation. This is our chapter 9, and recall in chapter 7 we looked at the cathode rays, and we saw that when we hit a metal, then the metal ejects electrons through thermionic emission. Then when you look at our chapter 8, when we mentioned about X-rays, one property of X-rays that we saw is that it causes photoelectric effect, but we didn't really go deep to see what is this photoelectric effect. Also, when we are looking at electromagnetic radiations, when we looked at the ultraviolet waves, the gamma rays, we saw that these waves do cause photoelectric effect. So what is this photoelectric effect? When we take a metal surface, recall, if we are to hit this metal surface, then it ejects electrons. Using it, the electrons absorb that heat energy and they are rejected, or they move away from the atom that is holding them. Then when we do that using heat, then we call that thermionic emission. If we take radiation, a radiation energy, and when we talk of radiation, we are talking of the electromagnetic radiation. In this case, when this is a metal surface, and then we shine a radiation on it, and this radiation must be of sufficient energy. The radiation right now that I'm talking about is a radiation like the UV radiation, ultraviolet, the X-rays, and the gamma rays. When we shine these radiations on the metal surfaces, now that they do possess energy, we found that the energy of a radiation is given by the Planck's constant times the frequency of that radiation. When we shine a radiation on the metal surface, then the electrons are able to absorb that energy of the radiation and they get ejected from the metal surface. In this case now, we are ejecting the electrons using the energy of a radiation. Again, when we take oxides of some metals, remember, when you look at the radiations we have here, you notice these are radiations in the electromagnetic spectrum that are above the visible light. When we take some oxides, some metal oxides, and on it we shine visible light. This is visible light. This is light of lower frequency than UV radiation, therefore it has less energy compared to this. But when we shine the visible light on some metal oxides, then also electrons are ejected from this metal surface. So please note that for pure metals, we are talking of radiations. For oxides, that is the strong radiations, UV, X-rays, and the gamma rays. For metal oxides, we have a weak radiation, that is visible light, which is still able to eject electrons from the metal surface. Now that we are using energy of a radiation, the electrons that are ejected, we call them photoelectrons. These are photoelectrons, and the process of ejecting these electrons using energy of a radiation is what is called PhotoElectric effect. Remember, anything that is pertaining to light is known as photo. And because here we can see light energy can be used to eject the electrons, we can also use the radiation energy. Then the whole process of ejecting electrons using a radiation energy from a metal surface is what is known as photoelectric effect. Therefore, photoelectric effect is simply a process through which electrons are ejected from a metal surface using a radiation of sufficient energy. Next, we'll be looking at two demonstrations that we can use to really show that photoelectric effect takes place. One, we'll be using neutral plates. We'll take two metal plates. Here they are. We have metal plate B, and here we have metal plate A. We have the connecting wires. You can see in our circuit, we have a source of EMF. We have a dry cell here, and we have a galvanometer. Remember, the work of a galvanometer is one, to detect very small currents, and number two, to show the direction of current. So in this case, we'll be using it to detect presence of small currents. Between A and B, we have a gap. We will also use a Mercury lamp that can produce the ultraviolet rays, and we are directing these rays on metal plate A. And we'll also need a glass pane. We'll see its work in this demonstration. Therefore, as it stands, without these radiations, if we don't have the UV radiation, there is a gap here. And therefore, as current flows, we don't expect a complete circuit, and therefore the galvanometer will be pointing at the zero mark. But when we shine a radiation, a UV radiation on metal plate A, please note, it is on the plate that is connected to the negative terminal of the cell. When this happens, then you'll note that this galvanometer will deflect. It will show a deflection. And the deflection simply means there is a registered current that has flown in the circuit. When we take the glass pane and we put it on the path of the UV rays so that we block them, then the glass pane is able to absorb all the UV radiations, and this galvanometer is seen to come back to zero. But without the glass pane, there is a registered current. When we place the glass pane along the path of the radiation so that the UV radiations are blocked, then we don't register any current. Therefore, there is something that this UV radiation is doing that is making that current to be registered. And what's happening is, when this radiation strikes the metal surface, electrons are rejected. Photoelectric effect takes place. When photoelectric effect takes place, then these electrons that have been ejected, plate B is connected to the positive terminal. Electron is negatively charged, and therefore they are attracted towards B. Then they close this gap and a current is registered in the circuit. The current will be small because of the number of electrons that are being ejected from plate A. But on blocking that, nothing happens. That means that the UV radiation has caused electrons to be ejected from plate A, and therefore photoelectric effect has taken place. What we produce here are the photoelectrons. What would have happened if this radiation was shown on B? Then on B, this is the positive terminal. So the electrons that will be ejected will simply be attracted back to the plate, and therefore the gap would not be closed. Therefore the radiation is shown on the metal plate that is connected to the negative terminal. So this is using two neutral plates, and we can see we are using a UV radiation to cause photoelectric effect. Another demonstration that we can use to show photoelectric effect is using a charged electroscope. We can take a mercury lamp. This is a mercury lamp. The mercury lamp has mercury vapor, which is able to produce UV radiation. And on it, we have an electroscope. You can see this electroscope is negatively charged, and that is why the gold leaf is diverged. Then on this electroscope, on the brass cap, this is the brass cap, we place a zinc metal. This is a zinc plate. So when we place it there, definitely we expect the charges to occupy the upper surface of the zinc metal. Then we are shining a UV radiation on this zinc plate. The zinc plate placed on the brass cap of a negatively charged electroscope. Then in case B here, we have an electroscope, but this time around, this is the UV radiation. The UV radiation is being shown on the zinc plate placed on a positively charged electroscope. It will be observed that on the negatively charged electroscope, the leaf is going to reduce in deflection, and with time, the leaf will fall. That is for the negatively charged electroscope. But for the positively charged electroscope, there will be no change in the divergence. I repeat that. For the negatively charged electroscope, this leaf will reduce in divergence, and finally with the time, the leaf will fall. Why does the leaf of an electroscope fall? When it is discharged. That is, when it becomes neutral. So there will be an effect of neutralization in this negatively charged electroscope. But in this case, there will be no effect. The divergence of the leaf will not change. Why is it so? When we shine the UV radiation on this zinc metal, which is placed on the negatively charged electroscope, then electrons are ejected through photoelectric effect. Remember, we are ejecting these electrons from the atoms on the zinc metal. When this electron is ejected, it leaves behind a positively charged, a positive charge, an ion that is positively charged. This positive charge that has been left, remember immediately an electron is emitted, there are negative charges on the zinc metal. So they are repelled. So the electrons will be repelled away. The positive charges that have been left, they will neutralize the negative charges. And therefore, as we continue shining the UV radiation on this negatively charged electroscope, as more electrons are repelled, more positive charges are being created, and therefore the negative charges already existing on this electroscope will be neutralized. And that is why the divergence here reduces, and finally the electroscope becomes totally discharged. What will happen in a positively charged electroscope? Well and good, the same thing. Here we have the atoms on the zinc metal. When this UV radiation is shown on the atoms of this zinc metal, the electrons are ejected. But they are already existing positive charges. Therefore, when this electron is ejected and it is negatively charged, it is immediately attracted by the positive charge next to it. This positive charge, it becomes neutral. But we have created another positive charge where that electron has moved from. This is an atom here. It ejects an electron. When it ejects an electron, it is left positively charged. But that electron is immediately attracted by another positive charge next to it. So what are we doing? We are creating one positive charge and neutralizing another. And therefore, at the end of the day, there will be no net charge. That is, the net charge will be zero, because we are creating as many charges as we are neutralizing. And in that case, that means that in this positively charged electroscope, there will be no change in divergence. Therefore, to show that is the photoelectric effect, then we can demonstrate it using a negatively charged electroscope. So this is photoelectric effect. We can use the two methods or the two demonstrations to show that really photoelectric effect takes place. So simply, photoelectric effect is the process through which electrons are ejected from a metal surface, either using a radiation energy or the light energy. So we'll meet in the next session, where we'll be looking at the light energy quantum theory.